Another version of you is making a different choice at this very moment. That is the staggering promise of parallel universes, a concept once confined to science fiction, but now a serious frontier of science. By the end of this exploration, you will understand 25 compelling reasons why leading physicists and cosmologists believe our reality is just one page in an infinite cosmic library. We will confront quantum experiments where cats are both alive and dead, uncover cosmic bubbles born from eternal chaos, and question if our entire existence is a simulation. The journey stretches from the subatomic to the edge of everything, challenging everything we assume about reality itself. What single idea about the universe feels the most real to you? The most startling evidence for parallel worlds comes not from telescopes, but from the baffling behavior of the smallest things in existence. At the quantum level, particles exist in a ghostly state of multiple possibilities, called superposition. To illustrate this strangeness, physicist Erwin Schrödinger proposed a famous, if grim, thought experiment. Imagine a cat sealed in a box with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the counter triggers and releases the poison, according to standard quantum theory, until someone opens the box and looks. The atom exists in a superposition of both decayed and not decayed states. Therefore, the cat is, in a very real mathematical sense, both alive and dead at the same time. It is only the act of observation that forces the universe to choose one definite outcome. This is the Copenhagen interpretation, and for decades, it was the accepted view. But that idea, that consciousness somehow collapses reality, left many scientists deeply unsettled. Why should the universe care if we are looking? In 1957, a young graduate student named Hugh Everett offered a radical and elegant alternative. He proposed that the universe does not choose. Instead, every single possible outcome of a quantum event actually happens. In one branch of reality, the atom decays and the cat dies. In another, perfectly real branch, it does not and the cat lives. There is no collapse because both outcomes continue to exist, just in separate, non-communicating universes that split off from one another. This is the many worlds interpretation. Every quantum decision, from the decay of an atom to the firing of a neuron in your brain, causes reality to continually branch into a vast, ever-growing tree of alternate histories. This idea solves the observer problem with breathtaking simplicity. There is no special role for consciousness. The math works perfectly without adding anything extra. For many physicists, this sheer mathematical cleanliness is why they find the idea so compelling. It suggests our universe is not a single narrative, but an endless library where every story that could be written is being written somewhere. But quantum branching is not the only path to parallel worlds. Our entire cosmos may be just one bubble in a frothing sea of universes. This startling idea emerges from our best theory of the Big Bang itself, a process called cosmic inflation. In the first fleeting fraction of a second after the beginning, scientists believe space itself underwent an unimaginable expansion, inflating from a subatomic speck to something astronomically large, faster than the speed of light. This explosive growth smoothed out the early universe, explaining why it looks so uniform in every direction we look. Yet the most profound implication of inflation is not how it started, but how it might never truly end. This leads to the theory of eternal inflation. Picture a vast, seething ocean of pure, hyper-expanding space. In most regions, inflation eventually slows and stops, allowing a stable universe like our own to form from the energy. But like a pot of water on a rolling boil, other pockets of this primordial soup continue to inflate at a frantic, eternal pace. Wherever inflation stops, a bubble universe pops into existence, floating in an ever-growing ocean of still inflating space. Each of these bubbles is a separate, self-contained cosmos, potentially with its own unique set of physical laws and constants. In one bubble, gravity might be 10 times stronger. In another, atoms could never form. Our universe, with its perfect balance allowing for stars, planets, and life, is simply one bubble where the conditions were just right. This is not science fiction, but a direct, albeit mind-bending, prediction from our most successful cosmological models. It suggests a multiverse of staggering scale, where new universes are being born all the time, forever. This perfect balance of our universe is not just a lucky break. It is a profound mystery that keeps scientists awake at night. Consider the fundamental forces that govern reality. The strength of gravity, the power of the nuclear forces, the mass of an electron. If any of these numbers were altered by even a tiny fraction, the universe as we know it would cease to exist. Stars would not form, atoms would fly apart, and complex chemistry, the very foundation of life, would be impossible. This is the fine-tuning problem. It feels as though the dials of creation were set with exquisite, impossible precision, just for us. The odds against this happening by random chance are astronomically small, like tossing a coin and having it land on its edge 1 billion times in a row. So why is our universe so perfectly suited for life? One compelling answer is the anthropic principle. In its simplest form, it states that we can only observe a universe capable of producing observers. It sounds almost like a tautology, but its power comes when paired with the multiverse. If eternal inflation is true, and there are an infinite number of bubble universes, each with its own random set of physical constants, then most of those universes will be sterile and empty. Some will have gravity too strong and collapse instantly. Others will have forces too weak to ever bind atoms. But in a vast enough landscape of possibilities, a few rare universes will, by pure chance, have the numbers line up just right. We are not in a special, designed universe. We are simply in one of the very few where the conditions allow us to be here to ask the question. The multiverse turns a miracle into a statistical inevitability. The eerie fine-tuning is not evidence of a creator, but a signature of our cosmic address in an infinite ensemble of worlds. The fine-tuning of our cosmos finds a potential explanation in the deepest mathematical framework physicists have ever conceived. String theory is the audacious attempt to unify all the forces of nature, from the gravity that holds galaxies together to the quantum glue binding atoms, into one elegant set of equations. It proposes that the fundamental building blocks of reality are not point-like particles, but unimaginably tiny, vibrating loops of energy called strings. The way a string vibrates, much like the different notes on a guitar string, determines whether it manifests as an electron, a quark, or a particle of light. For this beautiful symphony of mathematics to work, however, the universe must have more room than we can see. The equations of string theory only balance in a space of 10 or 11 dimensions. We experience only 3 of space and 1 of time. So where are the others? Scientists believe these extra dimensions are curled up, or compactified, on a scale so minute we could never perceive them directly. Think of a garden hose. From a distance, it looks like a simple one-dimensional line, but up close, you see it has a circular, two-dimensional surface wrapped tightly around its length. Our reality may be similar, with 6 or 7 extra dimensions coiled into complex, microscopic shapes. Here is where the multiverse emerges with staggering force. The mathematics shows there is not just one way to curl up these extra dimensions. There are an astronomical number of possible configurations, each resulting in a different set of physical laws for the universe it defines. The number of possible solutions is estimated to be 10 to the power of 500. That is a 1 followed by 500 zeros, a number so vast it exceeds all the atoms in our observable universe. This is the string theory landscape. It is not a physical place, but a mathematical map of every possible stable universe that the theory allows. Our universe, with its specific particle masses and force strengths, is simply one point on this colossal landscape. The theory does not predict a single, unique reality. It predicts a near infinity of them. For many theorists, this mathematical conclusion is not a bug, but a feature. It suggests that the quest for a single, perfect theory of everything might instead reveal a framework for everything that could possibly be. This spooky connection between particles points to a reality far stranger than simple branching. Quantum entanglement is a phenomenon so bizarre that Albert Einstein himself famously dismissed it as spooky action at a distance. It occurs when two particles, like photons or electrons, become intimately linked. Their quantum properties, such as spin or polarization, become intertwined regardless of the distance separating them. If you measure the spin of one entangled particle and find it pointing up, you instantly know its partner, even if it is on the other side of the galaxy, is pointing down. This correlation is instantaneous, seemingly violating the cosmic speed limit set by the speed of light. How can information travel faster than light? This is the heart of the mystery. The standard interpretation suggests the particles have no definite state until measured, and the act of measurement on one forces the other into a complementary state, no matter the distance. This non-locality, this ghostly link, suggests space itself might be an illusion, or that information travels through a dimension we cannot perceive. One compelling interpretation, proposed by physicist David Bohm, offers a radical picture. Bohm's pilot wave theory suggests particles are not ghostly probabilities, but real objects with definite positions at all times. However, they are guided by a hidden wave, a pilot wave that pervades all of space. This wave carries information about the entire experimental setup instantaneously. When two particles become entangled, their pilot waves become interconnected, creating a single, non-local guiding field. In this view, the particles are like boats being steered by a single, invisible current that connects them across any expanse. This implies a deeper, hidden level of reality, an implicate order beneath the world we see, where everything is fundamentally connected. While entanglement does not directly prove parallel universes, it shatters our classical intuition of a single, objective, and local reality. It shows that the universe operates on rules where influence can bypass space, and where objects can be part of a unified whole, even when separated by light years. This profound weirdness forces cosmologists to consider frameworks where our three-dimensional space is embedded in something much larger and more complex. A foundational idea that makes the multiverse seem less like fantasy and more like a necessary feature of a truly coherent cosmic theory. Black holes are not just cosmic vacuum cleaners. They are the ultimate paradox. Their immense gravity warps space and time so completely that nothing, not even light, can escape once it crosses the event horizon. This presents a catastrophic clash between our two great theories of reality. Einstein's general relativity, which describes gravity and the large-scale structure of the cosmos, says that anything falling into a black hole is lost forever, its information erased from our universe. Yet quantum mechanics, the rulebook for the small, has a sacred law: information cannot be created or destroyed. It can only be transformed. So which is right? Does a black hole truly destroy the history of a star, a planet, or a book, violating a fundamental quantum rule? This is the black hole information paradox, and its resolution points toward a reality that is fundamentally illusory. To solve it, physicists like Leonard Susskind and Gerard T. Hooft proposed a revolutionary idea, the holographic principle. It suggests that all the information contained within any volume of space, including every atom, every thought, every event that happens inside it, is not stored within that volume at all. Instead, it is perfectly encoded on the two-dimensional boundary that surrounds it, like a cosmic barcode painted on the surface of the event horizon. Our three-dimensional reality, with all its rich depth and detail, could be a holographic projection from information stored on a distant, two-dimensional surface. This is not a metaphor. It is a serious mathematical proposal about the fabric of spacetime itself. But this creates another dizzying puzzle, the black hole firewall paradox. If information is preserved on the horizon, what happens to an astronaut falling in? From the outside universe's perspective, their information is smeared onto the horizon, a fate resembling a fiery wall of energy. Yet from the astronaut's perspective, according to relativity, they should pass smoothly through the horizon, noticing nothing special. Both viewpoints cannot be true in a single universe. One radical solution is that the information is duplicated. The original information of the astronaut continues into the black hole's interior, while a perfect copy remains encoded on the horizon. But quantum mechanics forbids perfect copying. The only consistent way to resolve this is if the two copies exist in causally disconnected regions of reality, effectively in separate universes. The act of crossing a black hole's event horizon may not be a journey of destruction, but a branching point, splitting one history into two, with one version of events playing out on the surface and another, utterly inaccessible one, unfolding within. The black hole, therefore, becomes a natural machine for generating parallel realities. Its terrifying gravity not an end, but a gateway to another branch of the cosmic tree. The accelerating expansion of our universe is driven by a force so strange it defies all intuition. We call it dark energy, and it is the dominant component of the cosmos, making up nearly 70% of everything that exists. Yet we know almost nothing about it. This mysterious energy is woven into the fabric of space itself, causing it to stretch at an ever-increasing rate, pushing galaxies apart on a cosmic scale. The most baffling part is not its existence, but its value. According to our best theories, dark energy should be astronomically stronger than what we observe, by a factor of 1 followed by 120 zeros. Its actual measured strength is unbelievably, inexplicably tiny. This is not just a small discrepancy, it is the worst prediction in the entire history of physics. Why is the force shaping the fate of our universe so peculiarly weak? The multiverse offers a startlingly elegant answer. In the landscape of eternal inflation, each bubble universe crystallizes with a random value for dark energy. In the overwhelming majority of these bubbles, the value is enormous. In those realities, the repulsive force of dark energy is so powerful that it tears space apart almost instantly. Galaxies never get a chance to coalesce from the primordial gas. Stars never ignite. and the universe remains a forever empty, accelerating void. But in a vanishingly rare subset of bubbles, through sheer random chance, the value of dark energy is exceptionally small, like the one we find ourselves in. In these special cosmic neighborhoods, gravity has just enough time to pull matter together over billions of years. Galaxies form, stars are born, and around those stars, planets can coalesce. Only in such a bubble could observers ever arise to look up and wonder about the force that is now gently pushing their cosmic neighborhood apart. Our universe's bizarrely small dark energy is not a finely tuned accident. It is a cosmic selection effect. We could not possibly find ourselves in a universe where it was any different, because such a place would be eternally dark, empty, and silent. The very fact that we are here to measure it is a profound clue that our reality is one rare, habitable island in a vast and mostly lifeless multiversal sea. The quantum measurement problem cuts to the very heart of what reality is. When a particle exists in a superposition, as both here and there, what magical process forces it to pick a single location the moment we look? This is not a minor technicality. It is the central mystery of quantum mechanics. The traditional answer, the Copenhagen interpretation, insists that the act of observation by a conscious observer collapses the wave function, making one possibility real and erasing all others. But this raises more questions than it answers. What qualifies as an observation? Does a camera count? A rock? A single-celled organism? At what precise point does probability solidify into fact? The theory provides no clear mechanism, leaving a vague, almost mystical role for consciousness at the center of physics. It feels like an incomplete recipe, a rule added by hand because we did not like the alternative. And the alternative, proposed by Hugh Everett, is both shocking and beautifully simple. The many worlds interpretation states that the wave function never collapses at all. There is no special moment where probability becomes certainty. Instead, every single possible outcome contained within the quantum math becomes real. The universe does not choose, it splits. When you measure that particle, one version of you finds it here, and another, equally real version of you, in a newly branched universe, finds it there. The measurement problem simply vanishes. There is no longer a need for an extra rule about observation, no mysterious collapse, and no privileged role for consciousness. The mathematics flows smoothly and deterministically, describing a reality that continually branches like a growing tree. This is a powerful reason to take parallel universes seriously. It is not being proposed to create a more exciting cosmos, but to solve a profound conceptual headache with the most elegant tool available, the equations themselves. The multiverse, in this view, is not an add-on. It is the cleanest interpretation of the quantum rules we already have. It suggests that the strangeness we see in the lab is not a quirk of tiny particles, but a fleeting glimpse of the infinite, branching structure of everything. The idea that our universe is not the ultimate reality, but a sophisticated digital construct, is a modern twist on an ancient philosophical puzzle. Could everything we see, touch, and experience be the product of an advanced simulation, running on some unfathomable computer in a higher level of existence? This is the simulation hypothesis, and while it sounds like pure science fiction, it is taken seriously by a growing number of technologists and philosophers. The argument, popularized by figures like Nick Bostrom, follows a chillingly logical chain. First, assume it is possible for a sufficiently advanced civilization to create a high-fidelity simulation of a universe, complete with conscious beings inside it. Given the staggering potential of future computing power, this seems plausible. Second, if such a capability exists, it is reasonable to think that this civilization would not run just one simulation. They might run millions, billions, or even trillions of them, perhaps for research, entertainment, or historical preservation. This leads to a simple statistical conclusion. The number of simulated universes would vastly outnumber the one single base reality that created them. Therefore, if you are a conscious being wondering about your origins, the odds are overwhelmingly high that you are living inside one of those countless simulations, not in the original physical universe. This framework creates a unique kind of multiverse. Each simulation is, in effect, a self-contained parallel reality. The programmers could tweak the fundamental laws of physics for each one, experimenting with different constants or even adding their own Easter eggs. Glitches in our own reality, like the strange results of quantum experiments or the inexplicable nature of consciousness, could be seen as artifacts of the code or processing limitations in the cosmic computer. While we have no direct evidence for this, the hypothesis forces us to confront a profound question. If our universe is a simulation, then what lies outside it? An infinite stack of deeper realities, each running simulations of their own. This digital multiverse is a haunting mirror to the cosmological one, suggesting that parallel worlds might not be born from quantum branching or cosmic inflation, but from the deliberate, creative act of an intelligence we may never comprehend. Our cosmic vision is imprisoned by the very speed of light. We call everything we can possibly see the observable universe, a sphere centered on Earth with a radius of about 46 billion light-years. This is not the edge of existence. It is simply the limit of our information. The distance light has had time to travel since the Big Bang. Beyond this horizon lies more universe, likely stretching on for distances that dwarf our imagination. And if space is truly infinite, or near infinite, the implications are staggering. In an endless cosmos with a finite number of ways to arrange particles, patterns must eventually repeat. Think of shuffling a deck of cards forever. Eventually, you will get the same sequence twice. Now scale that up to the universe. Given enough space, the random quantum fluctuations that seeded galaxies will, somewhere far beyond our horizon, produce an arrangement of particles identical to our entire Milky Way, our solar system, and even this planet. Somewhere out there, a perfect copy of you is listening to this same script, in a patch of cosmos forever out of reach. This idea leads to a bizarre but logical consequence: the concept of Boltzmann brains. Named for the physicist Ludwig Boltzmann, it is a thought experiment about spontaneous order arising from chaos. In an eternal, infinite universe, it is statistically more likely for a single, fully formed conscious brain to spontaneously assemble from random particle collisions in the void, complete with false memories of a past life, than for an entire ordered cosmos like ours to evolve naturally. While scientists largely reject this as our actual origin, the fact we must argue against it highlights the profound weirdness of infinity. The existence of duplicate regions is not science fiction, but a direct mathematical prediction from cosmology and probability. It means the most intimate details of your life, every choice and memory, are not unique in an absolute sense. They are a pattern that, given enough canvas, the universe will paint again and again. Our observable horizon is not a wall, but a window into a single room of an infinite mansion, where every possible arrangement of matter and life plays out somewhere in the darkness. The elegant mathematics of string theory points toward an even grander unification, a master framework known as M-theory. Think of the 5 distinct string theories not as competitors, but as different windows into the same magnificent structure. M theory is the architecture that connects them all, revealing a cosmos of 11 dimensions where the fundamental strings are just one facet of a richer reality. Here, the building blocks can also appear as 2-dimensional membranes, or higher dimensional objects called brains, vibrating in this expansive spatial arena. This unified picture does not simplify the cosmic menu of possibilities. It explodes it. The landscape of stable configurations, or vacuum states, within M theory is vaster than anything we have yet conceived. Each possible way for those extra dimensions to curl and settle represents a distinct, stable vacuum. And each of these vacua is not an abstract equation. It is a recipe for an entire universe, dictating the number of particle families, the strengths of fundamental forces, and the very nature of matter itself. The number of these possible universes is not merely large. It is effectively infinite for all practical purposes. When you have a mathematical framework that allows for 10 to the 500 or more unique, self-consistent cosmic blueprints, the existence of our particular universe with its specific rules ceases to be a surprise. It becomes a statistical inevitability. In a landscape that immense, every possible set of laws that can exist does exist somewhere in the multiversal ensemble. Our reality, with its 3 generations of quarks and its precise electromagnetic force, is simply one point in this endless cosmic catalog. M theory does not predict a single universe. It demands a multiverse, making our existence not a lucky accident, but a guaranteed occurrence in the grand scheme of all possible things. The Big Bang presents us with a profound and unsettling question. Why did it start with such perfect, specific conditions? Our entire cosmic history, from the first stars to the planets that orbit them, depended on the universe being born with an exquisitely precise balance of energy, density, and expansion rate. If the initial push had been a fraction stronger, matter would have flown apart too quickly to ever clump into galaxies. A fraction weaker, and everything would have collapsed back in a catastrophic big crunch almost immediately. So why did our beginning have this golden ticket? A single, lonely universe offers no answer, only a miracle. But within a multiverse, the question itself transforms. Our Big Bang was not a singular, unique genesis of all reality. It was simply one event, one bubble nucleation, in a much larger and possibly eternal meta-universe. In this grander arena, different regions can inflate with wildly different starting conditions. In most of those regions, the numbers are wrong, and the resulting universes are stillborn or barren. But in a vast enough ensemble of beginnings, a few will, by pure chance, have the right numbers for complexity and life to emerge. We do not live in a universe with a special, finely tuned birth. We live in the aftermath of a beginning that was ordinary and unremarkable within an infinite set of possibilities. The multiverse removes the burden of explaining a 1 in a quintillion lucky break by making it a statistical certainty. Our cosmic story did not start with a miracle. It started with a roll of the dice in a casino that never closes. The bizarre rules of the quantum world refuse to stay in their tiny box. For decades, we comforted ourselves with the idea that superposition and entanglement were quirks of the microscopic, that once objects got big enough, the familiar, solid world of classical physics would take over. But what if that boundary does not exist? Recent experiments have shattered that comforting illusion, pushing quantum weirdness into a realm we can almost see. Scientists have successfully demonstrated wave-particle duality, the hallmark of quantum superposition, with molecules composed of thousands of atoms. These are not single electrons, but complex structures large enough to be seen under powerful microscopes. In a stunning experiment, researchers sent a molecule called phthalocyanine, shaped like a tiny propeller, through a double-slit apparatus. Just like photons or electrons, the molecule produced an interference pattern, proving it had traveled through both slits at once as a wave of probability. This was not a microscopic particle, but an object visible in its own right, behaving in two places simultaneously. The quest goes further, aiming to create a true Schrödinger's cat scenario with a tiny but macroscopic vibrating membrane or a small mirrored bead suspended in a vacuum. The goal is to place such an object into a superposition of two distinct states of motion, like vibrating and not vibrating at the same time. If achieved, it would mean an object you could theoretically hold on your fingertip would exist in two contradictory realities until measured. This erases the imagined line between the quantum and classical worlds. If a molecule with thousands of atoms obeys quantum rules, why not a grain of sand? Why not a cat? The Copenhagen interpretation struggles here, unable to define where observation begins. Does a single photon bouncing off the object count as a measurement? The many worlds interpretation, however, glides past this confusion with elegant simplicity. It does not need a special rule for when things get big. The mathematics applies equally to an electron and a planet. In this view, the vibrating bead does not mysteriously choose one state when we look. The entire universe simply branches to accommodate both possibilities. The fact that quantum effects persist at larger and larger scales makes this branching reality not just a philosophical preference, but the most consistent explanation for a universe that refuses to be split into two sets of rules. The success of a theory is measured by its predictions, and cosmic inflation has passed every test with flying colors. Its most stunning triumph is its explanation of the cosmic microwave background, the faint afterglow of the Big Bang that fills the entire sky. Before inflation, scientists were puzzled by this ancient light. No matter which direction we look, the temperature of this radiation is almost perfectly uniform to about 1 part in 100,000. This presented a huge problem because in the standard Big Bang model, distant regions of the universe would never have had time to exchange heat and reach this equilibrium. It would be like walking into a vast room where the temperature in every corner is exactly the same, even though the heaters on opposite walls have never been connected. Inflation solves this by proposing that the entire observable universe was once a microscopic, ultra-dense region where everything was in intimate contact. That tiny patch then underwent a period of hyper-expansion, stretching that initial uniformity across the entire cosmos we see today. But inflation predicted more than just smoothness. It forecasted that quantum fluctuations from that primordial seed would be stretched to cosmic scales, creating tiny ripples in density. These ripples are the blueprints for all future structure, the gravitational seeds for galaxies and galaxy clusters. When satellites like the Cosmic Background Explorer and the Planck spacecraft mapped the CBM with exquisite precision, they found exactly the pattern of fluctuations that inflation had predicted decades earlier. This is not a vague suggestion. It is a precise, quantitative match that stands as one of the greatest successes in modern cosmology. And here is the crucial link to parallel worlds. In most viable models, once you have the mechanism for a short burst of inflation that creates our universe, you almost inevitably get eternal inflation. The same quantum processes that seeded our galaxies can also cause some regions of space to continue inflating forever, spawning new bubble universes in an endless chain. The theory that so perfectly explains the oldest light in our sky does not naturally lead to a single, lonely cosmos. It points toward a fecund, self-replicating multiverse. The empirical success of inflation, therefore, is not just evidence for our own beginning. It is a compelling hint that our beginning was anything but unique. The equations that govern the quantum world do not whisper of a single, definitive reality. They sing in harmonies of possibility, describing not one outcome but a symphony of them. This is the core argument from theoretical physics for parallel timelines. The mathematics of quantum mechanics, in its purest form, does not contain a special command for wave function collapse. That rule, which says probabilities solidify into a single fact upon observation, was added later, almost like a patch to make the theory fit our classical intuition. In the many worlds interpretation, you simply remove that patch. You take the equations at face value and let them run without interruption. What you find is that they naturally, inevitably, describe a reality that continuously branches. Every term in the quantum wave function, every possible outcome, continues to exist. The math does not forbid parallel timelines. It generates them with elegant consistency. For many physicists, this is a powerful reason to take the idea seriously. A good scientific theory should be as simple as possible, yet explain everything we see. This principle is known as Occam's razor. In this light, which is simpler, a theory where the math works perfectly but describes a vast, branching multiverse, or a theory where we must append an extra, unexplained axiom about conscious observation to force the math to match our limited experience. The many worlds view argues for the former. It suggests that the parallel timelines are not an extravagant addition, but are already embedded in the equations we have trusted for a century. They are not a bug in the code of reality, but a feature we have been reluctant to see. The profound silence of the cosmos is itself a message. Enrico Fermi posed the famous question, if the universe is so vast and old, with billions of potentially habitable planets, then where is everybody? This is the Fermi paradox, and its unsettling quiet has spawned dozens of solutions. One of the most intriguing is the cosmic zoo hypothesis. It suggests that advanced galactic civilizations do exist, and they are aware of us, but they have chosen to place our young, developing world under a kind of observational quarantine. They do not interfere, broadcast signals, or reveal their megastructures, allowing humanity to evolve naturally without outside influence. This could be a universal ethical principle, a prime directive observed by countless civilizations across the galaxy. But the multiverse adds a deeper, more chilling layer to this idea. If eternal inflation is true, creating a boundless array of bubble universes, then intelligent life is not a rarity, it is a cosmic commonplace. In such a landscape, the rules of engagement between civilizations might be codified into a fundamental framework, a multiversal law. Perhaps contact is forbidden until a species reaches a specific technological or ethical maturity, a filter we have not yet passed. Or consider the simulation hypothesis again. If our reality is a constructed simulation, the silence could be a deliberate programming constraint. The architects of the simulation may have built in a firewall, preventing simulated civilizations from detecting their creators or each other, to maintain the integrity of the experiment or for reasons we cannot fathom. Our cosmic loneliness, therefore, might not be evidence of our uniqueness, but a clue about the architecture of a much larger reality. The empty sky is not a sign that we are alone, but a potential indicator that we are part of something far more complex and regulated than a single wild universe. The silent sky may hold its secrets, but in laboratories around the world, a new kind of machine is screaming a different truth. Quantum computers are not science fiction. They are being built right now, and their very existence leans on the reality of parallel possibilities. These devices harness the two most bizarre features of quantum mechanics, superposition and entanglement, to perform calculations that would take a classical computer longer than the age of the universe. But how do they work? A classical computer bit is like a simple light switch, either definitively on or off, representing a 1 or a 0. A quantum bit or qubit is like a switch that is both on and off at the same time. This is superposition in action. By placing a qubit in this blended state, it can hold and process multiple potential answers simultaneously. When you entangle a group of qubits, their fates become intertwined, creating a vast, interconnected web of superposed states. This allows a quantum computer to explore a near-infinite landscape of possibilities in a single computational step. While this does not directly prove the many worlds interpretation, the operational success of these machines is a powerful form of evidence. Engineers are not building devices based on vague probabilities or mathematical tricks. They are manipulating what they treat as real, coexisting states of reality. The qubit is not almost 1 and almost 0, it is both, and the computer uses that literal duality to find solutions. This practical, engineering-level acceptance of quantum multiplicity makes it far more difficult to dismiss superposition as a mere lack of knowledge. If you can build a machine that relies on an electron spinning in two directions at once to crack an encryption code or model a complex molecule, you are, in a very tangible sense, treating parallel realities as a usable resource. The quantum computer is a tool that reaches into the branching tree of possibilities and pulls out an answer, suggesting that those branches are not just mathematical abstractions, but a foundational layer of the cosmos we can now learn to engineer. This logical conclusion from infinity is both comforting and deeply unsettling. If the universe truly has no end, and matter is spread more or less evenly throughout, then a profound statistical truth emerges. With a finite number of ways to arrange particles, but an infinite canvas on which to arrange them, every single possible pattern must occur not just once, but an infinite number of times. Think of it like this. If you give a monkey an infinite amount of time to type on a keyboard, it will eventually, by pure chance, produce the complete works of Shakespeare. Now, replace the monkey with random quantum fluctuations across an endless cosmos. Replace the typewriter with the fundamental building blocks of reality. In an infinite universe, the monkey does not just type Shakespeare once. It types every possible book, every poem never written, and every version of this script with a single word changed, an infinite number of times over. This is what cosmologist Max Tegmark calls a level 1 multiverse. It is not a separate dimension or a quantum branch, but simply regions of our own infinite space, so vastly distant that light from them has not and will never have time to reach us. Within this framework, the implications for your own existence are staggering. Somewhere beyond our cosmic horizon, there is a galaxy identical to the Milky Way. Orbiting an identical sun is an identical Earth. On that planet, a person who is you, with all your memories and experiences up to this exact moment, is listening to these words. But infinity does not stop at one copy. It demands every variation. In another region, a version of you chose a different career path. In another, you never met your closest friend. Every decision you did not make, every path you turned away from, is being lived out in full by another iteration of yourself in a distant, unreachable part of the cosmos. This is not science fiction, but a direct, inescapable consequence of infinite space and the laws of probability. The universe, in its limitless expanse, becomes the ultimate library of all possible stories, with every life a sentence written over and over again across the endless pages of reality. It suggests a cosmos where nothing is truly unique, only infinitely repeated. Our relentless march from past to future feels like the most fundamental law of existence. Yet physics tells us this arrow of time is not written into the basic equations of the universe. Those equations work perfectly well in reverse. So why do we remember yesterday but not tomorrow? The answer lies in a concept called entropy, a measure of disorder. The second law of thermodynamics states that the total entropy of an isolated system always increases over time. Think of a drop of ink in a glass of water. It starts as a neat, ordered drop, but it will always spread out into a uniform, disordered mixture. That process defines the arrow of time for us. The universe started in an astonishing state of incredibly low entropy at the Big Bang, a condition of exquisite order. Everything since has been the cosmic ink drop spreading out, creating the flow of time we experience. But this presents a monumental puzzle. Why was the beginning of our universe in such a special, low entropy state? It is like walking into a room and finding every book perfectly shelved, every paper neatly stacked. The odds of that happening by chance are vanishingly small. A single universe offers no explanation for this miraculous starting point. The multiverse, however, provides a breathtakingly grand perspective. In an eternal, perhaps infinite, meta-reality, entropy can fluctuate. Most of the time, this larger system is in a state of maximum disorder, a featureless, timeless soup. But occasionally, purely by random chance, a tiny pocket will experience a statistical fluctuation into a state of lower entropy. Our Big Bang may have been exactly that, a rare, random eddy of order in an eternal sea of chaos. In this view, our entire cosmos, with its arrow of time pointing forward, is not the main event. It is a temporary bubble of structure that spontaneously emerged from a timeless, high-entropy background. This framework allows for even stranger possibilities. If our universe is one such fluctuation, there could be countless others. Some might have arrows of time pointing in the opposite direction from ours, where beings would perceive our future as their past. Others might exist in balanced, timeless states where entropy never changes, and cause and effect have no meaning. Our unidirectional experience of time, then, is not a universal constant. It is a local condition, a property of our specific cosmic bubble. We are not moving through time because the universe demands it. We are simply living inside a rare and temporary region where order is slowly, inevitably, dissolving back into the void from which it came. The holographic principle is not just a metaphor, it is a precise mathematical map. This map is known as the ad-SCFT correspondence, and it stands as one of the most profound discoveries in theoretical physics. Ad-S stands for anti-de Sitter space, a special type of universe with a constant negative curvature, like the surface of a saddle extending forever. CFT stands for conformal field theory, which describes the behavior of particles without any inherent scale, like a perfect, self-similar pattern. The correspondence, proposed by physicist Juan Maldesna, states a breathtaking equivalence. A theory of gravity operating within the entire volume of an anti-de Sitter space is completely and exactly equivalent to a quantum field theory living only on the lower dimensional boundary that encloses it. Think of a sealed, round fishbowl. Inside the bowl, you have stars, black holes, and the full force of gravity playing out in 3 dimensions. The correspondence proves that every single event inside that bowl, every orbit and collision, is perfectly mirrored by the interactions of tiny, quantum particles zipping across the 2-dimensional surface of the glass. Nothing is lost. The 3-dimensional reality is a perfect hologram projected from the data on the 2-dimensional boundary. For our universe, this suggests a staggering possibility. Our 4-dimensional spacetime, with all its galaxies and gravity, might be a holographic projection from information encoded on a distant, cosmic surface we cannot see. But the implications run even deeper into the multiverse. The ad-SCFT duality is a two-way street. If our universe has a holographic description, then the source code for our reality exists somewhere else, in a higher dimensional realm physicists call the bulk. Our entire cosmos, in all its rich detail, would be like a movie playing on a screen, while the true film reel exists in a projector in another room. That projector room, the bulk, could contain not just our universe, but many others, each with their own boundary screen. We would be one of many holographic shows running simultaneously in a grand, higher dimensional theater. This framework transforms the multiverse from a collection of separate bubbles into layers of a cosmic onion, where what we perceive as fundamental reality is merely a shadow cast from a more complex, hidden dimension. It suggests that searching for parallel worlds might require us to look not outward into space, but inward, into the very informational fabric from which our existence is woven. The deepest conflict in physics is a silent war between 2 incompatible rulebooks. On one side, quantum mechanics governs the realm of the incredibly small with flawless precision. On the other, Einstein's general relativity masterfully describes the gravity that shapes galaxies and the cosmos. Yet when these 2 theories meet at the heart of a black hole or the moment of the Big Bang, the math breaks down into gibberish. This is the quantum gravity conundrum, and every serious attempt to solve it seems to open a door to the multiverse. Take loop quantum gravity, a leading contender. It proposes that space itself is not a smooth, continuous fabric, but woven from tiny, indivisible loops, like a cosmic tapestry made of finite threads. In this framework, our Big Bang might not have been a singular beginning from nothing, but a big bounce. A previous universe could have collapsed under its own gravity, reaching a point of maximum density before quantum effects caused it to rebound, expanding outward into the cosmos we inhabit today. This cyclical model suggests an endless chain of universes, each born from the death of the one before it, a never-ending cosmic heartbeat. Another approach, causal set theory, describes reality as a collection of discrete events linked in a vast network, like grains of sand connected by threads of cause and effect. In such a model, the flow of time and the expanse of space are not fundamental, but emerge from the pattern of connections. And just as a network can branch, so too can spacetime itself, creating divergent histories from a single causal origin. Even within the more established path of string theory, the quest for quantum gravity leads to the same staggering conclusion. The mathematics that could finally marry the very small and the very large does not yield a single, unique universe. Instead, it reveals a landscape of stupefying possibility, where every stable solution of the equations corresponds to a different reality with its own laws. The multiverse, therefore, is not a fringe idea tacked onto physics. It is a recurring, almost inevitable theme that emerges when we push our theories to their absolute limits, seeking a unified description of all existence. It seems the cosmos, in its ultimate architecture, refuses to be alone. The human mind has been dreaming of other worlds for millennia, long before quantum physics or cosmic inflation entered the lexicon. Ancient myths spoke of shadow realms, spirit worlds, and lands of the dead existing alongside our own. Philosophers from Plato to Leibniz pondered the nature of possible worlds, realms where history unfolded differently. In every culture, storytelling has been saturated with the idea, from the dream worlds of indigenous shamans to the countless science fiction tales of alternate dimensions. This persistent, cross-cultural fascination is striking. It could be dismissed as mere fantasy, a psychological escape from the constraints of a single, linear life. But what if this recurring intuition points to something deeper? Some theorists suggest it is no accident. Our consciousness arises from the chemical and electrical chatter of billions of neurons, a biological system operating at a scale where quantum effects may play a role. If our brains are, even in a small way, quantum systems, then the fundamental multiplicity of the quantum realm might subtly influence the very structure of our thought. We might be hardwired to perceive reality not as a single thread, but as a tapestry of possibilities, because on some level, that is what we are. The stories we tell could be echoes of a truth our science is only now beginning to articulate. The multiverse is not a cold, mathematical abstraction. It is an idea that has lived in our collective imagination since we first looked at the stars and wondered what else might be out there, waiting in the spaces between. The persistent mystery of consciousness haunts the edges of quantum theory. If observation truly collapses the wave function, what or who counts as an observer? Is it a human scientist, a camera, a single-celled amoeba, or even a rock? The Copenhagen interpretation, for all its successes, provides no clear answer. It places something vague and seemingly non-physical, our awareness, at the very center of reality's machinery. This is deeply unsatisfying for a science built on material causes. It suggests that the solid world around us depends, in some inexplicable way, on being seen. This controversial link creates a paradox where mind and matter become entangled in a way that feels more like philosophy than physics. The many worlds interpretation cuts through this not with surgical precision. In this view, consciousness is not a magical catalyst that forces possibilities into a single fact. It is an emergent property of complex physical processes, a story written by the brain as it navigates one branch of an endlessly forking reality. When you look at a quantum experiment, you do not collapse anything. Instead, your conscious experience splits along with the universe. One stream of awareness sees the particle here. Another stream, belonging to a different version of you, sees it there. Both experiences are equally real, and both are the product of purely physical interactions. There is no special moment where consciousness intervenes, because the branching happens regardless. This removes the observer from a position of privileged mystery and places it firmly within the natural world. For physicists and philosophers seeking a complete physical account of existence, this is a powerful motivation to take parallel worlds seriously. The multiverse does not just explain quantum weirdness. It rescues science from a potential dead end, a universe that winks into being only when we pay attention. It offers a vision where reality is objective, vast, and independent, and where our precious sense of self is not the author of the cosmos, but one of its countless, beautifully written chapters. The most powerful scientific ideas are not those we accept on faith, but those we can put to the test. A common criticism of the multiverse is that it is untestable, a philosophical notion forever beyond the reach of science. Yet this is precisely where the story becomes most exciting, because scientists are not content with mere speculation. They are actively devising ingenious, if indirect, ways to hunt for evidence of other worlds. One of the most promising search grounds is the cosmic microwave background, that ancient afterglow of the Big Bang. If our universe is one bubble in a frothing sea of eternal inflation, it is possible that during its infancy, it bumped into a neighboring bubble universe. Such a cosmic collision would have left a distinct, asymmetric imprint on the CMB, a kind of bruise on the sky. Researchers have already combed through data from satellites like Planck, looking for unusual patterns or cold spots that could be the signature of such an encounter. While no definitive signal has been found, the search continues, refining what we should look for. Another potential clue lies in primordial gravitational waves, ripples in spacetime from the violent expansion of the cosmic inflation period. The specific pattern and strength of these waves, which future observatories hope to detect, could tell us about the energy scales involved in that early expansion. Certain signatures would strongly favor models of inflation that naturally lead to an eternal, bubble-producing process, making a multiverse far more likely. Even the quantum realm offers a testing ground. As we build more sophisticated quantum computers, we may be able to simulate simplified models of other quantum branches, or even the dynamics of bubble nucleation. By comparing the behavior of these simulations with our own universe's quantum rules, we could find supporting evidence for the underlying framework that generates multiple realities. The very fact that these empirical pathways are being mapped out transforms the multiverse from a philosophical idea into a serious scientific hypothesis. It is a puzzle with potential solutions, a mystery with clues we are learning how to read. This relentless drive to test the untestable is the heartbeat of real science, pushing at the very edges of what we can know. Ultimately, we are left with a profound and unifying reason for this entire journey. The human drive for understanding pushes us to seek not just descriptions, but a complete theory of reality. We yearn for a framework that explains everything, from the precise strength of gravity to the specific moment of the Big Bang, from the eerie randomness of quantum events to the very fact of our own existence. This is the scientific holy grail, a set of ideas that leaves no fundamental question dangling. And right now, the multiverse stands as the leading candidate to fulfill that deep intellectual need. It does not answer every question with a neat local answer. Instead, it reframes all of them. Why are the constants of nature fine-tuned? Because in an infinite ensemble of universes, some will, by chance, have the right numbers for life. Why did our universe begin with such low entropy? Because it is one rare fluctuation in an eternal, high-entropy background. Why does quantum mechanics present us with probabilities? Because every possible outcome actually occurs in a branching tree of realities. The multiverse embeds our single, seemingly special cosmos within a vast, often chaotic, but ultimately logical larger structure. It trades a collection of separate, miraculous accidents for one grand, overarching principle: the existence of all possible worlds. This is not a retreat from explanation, but an expansion of it on the grandest scale imaginable. For many of the brightest minds in physics, the strangeness of parallel universes is not a bug. It is the feature that makes everything else finally make sense. It offers a vision where our reality is not an inexplicable singularity, but a single note in an infinite cosmic symphony, playing all the melodies that mathematics allows. These 25 threads weave a single, breathtaking tapestry of possibility. From the quantum split that creates a new you with every decision, to the cosmic bubbles of eternal inflation. From the holographic codes on a distant boundary to the silent statistical scream of an infinite cosmos, each reason is a doorway. They are not wild speculations, but serious hypotheses born from our deepest scientific puzzles, our boldest mathematical frameworks, and our oldest human dreams. The multiverse remains unproven, a frontier of thought rather than a mapped territory, yet its very persistence across physics, cosmology, and philosophy reveals something profound about our quest to understand. It is the ultimate expression of a simple, powerful drive to look at the universe and insist that the story must be larger, stranger, and more magnificent than the single chapter we can see. Whether it is a mathematical necessity or a magnificent fiction, the idea that countless other realities might exist, with other lives, other histories, and other laws, stands as the grandest testament to human curiosity ever conceived. So what do you think? Which of these reasons resonates most with you? Or do you have a theory of your own about the nature of reality? Share your thoughts below. And if you are hungry for more journeys to the edge of understanding, be sure to subscribe. Our exploration of space mysteries has only just begun.